Okay, so last time we had started our section on isomorphisms, and we were talking about different kinds of isomorphisms. So we looked at the good old vector space linear isomorphisms, just bijective linear maps between vector spaces, and there we had no problems at all. If you had a bijective linear map from one vector space to another, then you could invert it and you got a linear isomorphism in the other direction. So if you had a linear isomorphism, you could just take the inverse map and you got a linear isomorphism back. So that was an easy exercise. And then there was a connection with Hamel bases, and that you just needed to check what was the cardinality of your Hamel basis to figure out the isomorphism class of your vector space, if you like. Now, norm spaces, really to be a sort of isomorphism of norm spaces, if you're working the category of norm spaces, you'll be looking at continuous linear maps. So you're really interested in isomorphisms which are continuous in both directions. And there's the irritating thing, that you could have a bijective linear map from a norm space to another norm space, and it could be continuous in one direction, but the inverse might be discontinuous, which is something that can happen for norm spaces, but not for Banach spaces. So I left you with an exercise, and this is, I think, on it's not on this question sheet, but it is on the next question sheet to actually do this. I wondered if anybody had already done it. Has anybody figured out an example of a norm space, a linear isomorphism between two norm spaces, which is continuous in one direction but discontinuous when you invert it? And you can go for a norm space to itself to do this. Anybody come up with an example? Well, I'll give you more time to think about that one. It will come up on the question sheet. As I say, C00 is a very useful supply of incomplete norm spaces. Put your favourite norm, whether it's L infinity norm or LP norm, but just restrict it to the C00, the sequences which are eventually zero, and you'll get an incomplete norm space. And you can do just about any example you like with that. So most of these results that are true for Banach spaces are false for C00. And you can easily come up with an isomorphism from C00 to itself with your favourite norm, which is continuous in one direction and discontinuous in the other. But we can always come back. If you still can't do that exercise once it's come up on the question sheet, let me know and we can always talk about it further. So isomorphic as norm spaces, I would insist on continuity in both directions. So if I say two norm spaces are isomorphic, I mean there is a vector space isomorphism which is continuous in both directions. So both the map and its inverse are continuous. And that, of course, means that they're vector space isomorphisms and that they're homeomorphisms, which is the topological version. And so you could call it a linear homeomorphism, which will incorporate everything. And then if you can't remember whether isomorphism includes all the things you need, then linear homeomorphism is safe. Now there's a stronger notion of isomorphism, known as isometric isomorphism, where you have a linear isomorphism so that the map is actually isometric. So that's slightly different, not hugely different though, because if you remember the fact that continuous implies bounded and for linear maps, and that means your Lipschitz continuous, then you only talk about the difference between being Lipschitz continuous in both directions. So that means not scaling up or down by distances by more than some constant or other, and actually keeping the distance exactly the same, which is what isometric isomorphisms do. So there's not much difference. There's only a constant in it. But it is a subtle difference, and it does make a difference. There are things around which are isomorphic, but not isometrically isomorphic, and you've just got that little bit more flexibility. And it really makes a surprisingly big difference when you're investigating spaces of continuous functions and trying to decide whether isomorphic to each other, which is quite often, and whether they're isometrically isomorphic to each other, which is very rarely. So actually, although there isn't much room in between, it's enough to make the difference for quite a large class of spaces. Anyway, so isometric linear isomorphisms or isometric isomorphisms are the ones where you've got this really tight constraint that distance is preserved exactly. Now, are these things genuinely different? Well, I've told you they are, but it'd be nice to have some examples, wouldn't it? Let's first have some remarks. Well, finite dimensions, any linear map from a finite dimensional norm space into a norm space is automatically continuous. It's not true that every linear map from a norm space into a finite dimensional norm space has to be continuous, because you can have discontinuous linear functionals. So it's the one you're coming from that matters here. But if your domain is finite dimensional, then your linear map is automatically continuous, which is rather nice. There's an exercise on a question sheet to help you finish that one off. But so in particular, if you've got any linear isomorphism of finite dimensional norm spaces, then it's automatically an isomorphism of norm spaces in as much as it's continuous in both directions. So it's automatically a linear homeomorphism. And in metric space theory, there's a notion of isometry, but it doesn't have to be surjective. But if you're talking about a linear isomorphism, which is an isometry, then it is surjective. So then the inverse map is automatically an isometry as well. So inverses of isometric isomorphisms are also isometric isomorphisms. So isometric isomorphisms are better than just topological homeomorphisms, better than just the being continuous in both directions. So here you are, here's the claim. Every isometric isomorphism is a linear homeomorphism, because the inverse is another isometric isomorphism. Converse is false, but even better than that, there are spaces which are isomorphic as norm spaces, so linearly homeomorphic to each other, but which are not isometrically isomorphic. And the interesting thing is that that's a different statement. So let me see some examples of what could be going on here. Okay, so first of all, how can you get, what's going to be a nice example, given some of the facts I've just mentioned here, how can you come up with a nice example of something which is a topological homeomorphism, a linear homeomorphism, but not an isometric isomorphism? Actually, you can do that in a one-dimensional space. So what's going to be an example of a linear homeomorphism which is not an isometric isomorphism? So, a linear homeo which is not an isometric iso. Just to abbreviate. Well, you have to tell me a norm space and a linear map which is one but not the other. But your norm space could be one-dimensional. And I don't mind whether you use R or C. So, anyone want to suggest one? You can give me a one- or two-dimensional space, and you may as well map it to itself. In such a way that you get a linear homeomorphism In other words, it's a linear map, continuous in both directions, it's going to be an isomorphism of the vector space, but it shouldn't preserve distance exactly. That's exactly the one I was thinking of. Double everything. Yes, I wonder why you came up with 2. There you go. I suppose it's the smallest number bigger than 1, right? No, of course not. But nevertheless, that's exactly our example I was thinking of. Yes, so we'll do T from R to R, and the usual norm. The usual norm on R is norm x equals mod x, which is the usual modulus. I suppose if I had to tell you if I was going to have different kind of moduli, then I'd be in real trouble. I'd have to tell, but if I write modulus, I just mean standard modulus. And we'll have T of x equals 2x. Clearly continuous and linear and bijective, and T to minus 1 of x is equal to a half x. These are clearly both continuous and linear. Of course, because they're linear and it's a finite dimensional space, the continuity was automatic. However, it's particularly clear in this case. So it's clearly a linear isomorphism T and T to minus 1 are continuous, though that's, as I say, automatic. But it's not isometric, because in fact it's doubling distances. So that was easy. You can find a linear homeomorphism which is not an isometric isomorphism. But here's something very peculiar that can happen. Well, actually, this is already an example. This shows that R is, this is a linear map from R to R, which is a topological homeomorphism, which shows that R is which shows that R is isomorphic as a norm space to R. But it's clear that we've chosen the wrong linear map, because if we'd chosen a different one, we could have shown it was actually isometric to itself. We should have used the identity map here. If we'd used the identity map, we'd have shown the stronger condition that it was isometrically isomorphic to itself. A very unsurprising fact. Okay? Let's have a look at something slightly more interesting. Let's look at R squared with 2 different norms. This is one where the identity map is going to turn out to be the wrong map, and there's another map that's better. R squared with norm 1, and R squared with norm infinity. Let's call this first one, let's call that one x1, and this one x2. So that x1 and x2 are both sort of R squared, but with different norms. Okay? Now the identity map, id R squared, from x1 to x2, is a topological homeomorphism. A linear homeomorphism would be better. Okay, the identity map is obviously a linear isomorphism from R squared to itself. If you put different norms on R squared, then you can ask, is it continuous? But I've already told you it's bound to be. And anyway, we know that. We know that all norms on finite dimensional spaces are equivalent, which is basically the same thing. That's what I was claiming before. So this is a linear homeomorphism. The inverse, I suppose, it's still id R squared, but you could think of it as the inverse of id R squared if you want. Anyway, going from x2 to x1. So optional whether you put a to the power minus 1 at the top, since the inverse of the identity map is still the identity map. However, this time it's going from x2 to x1, and it's still continuous, and it's still a nice linear homeomorphism. But it's not an isometric isomorphism because the norms are different. But actually, these two norm spaces are isometrically isomorphic if you use a different map. It's a bit of a fluke, I think. But if you draw the unit balls for these, one of them is a square and the other is a diamond, and that will reveal that there is some connection between these two spaces. The diamond is just the square rotating through 45 degrees and expanded, or contracted. Yes, it's contracted by root 2. Which will give you a clue as to how you could define an isometric isomorphism between these, namely by scaling by a factor root 2 and rotating through 45 degrees. And that actually does give you an isometric isomorphism between these spaces. So here's an exercise to fill in the details of that. Exercise x1 and x2 are isometrically isomorphic using a different linear map. Get rid of that. Have another page. So as I said, look at the unit balls to see what's going on. Any isometric isomorphism must map the unit ball bijectively onto the other unit ball. And that's pretty much an if and only if. If you've got a linear map that does map the unit ball bijectively onto the other unit ball, then I think you'll find that you can prove that it is an isometric isomorphism as well. So that's a nice thing about linear maps, as usual. Okay, so finally then, you want two genuinely different ones where they aren't isometrically isomorphic. And so here's a further exercise. Show that R squared with norm 1 is not isometrically isomorphic to R squared with norm 2. Given some of the stuff I've just been saying, with geometrical intuition, though this is a bit tricky to turn this into a rigorous argument, though you can probably do it, R squared with norm 1 did turn out to be isometrically isomorphic to R squared with norm infinity because both balls were squares. So why is there no real chance that they could be isometrically isomorphic to R squared with norm 2? Yeah? Yeah, the unit ball is round. Okay? The unit ball in R squared norm 2 is round. But it's supposed to be your supposed linear isometric isomorphism is supposed to map this square onto a circle, but you can't map a square to a circle with a linear map. So you can convert that into a rigorous argument. But there are some other ways to do it as well. So I don't want to spoil your fun about thinking about various different ways to prove it. One way to do it, though, I'll give you a little hint. One way to do it. For example, if you're working in the one norm or the infinity norm, you can actually find a set of 4 points, each of which is at distance exactly 1 from all of the others. And that's rather difficult to do in R squared with the usual distance. Because once you've got 3 points all equidistant, they're already making an equilateral triangle. So where are you going to put the 4th point? Okay, so that's another way to do it. Now, isomorphic, this is something, remember, this is something that's better than with metric spaces. With metric spaces, homeomorphisms are not enough to identify completeness. But with linear maps, continuous is the same as Lipschitz continuous, and that means that you're better than just a homeomorphism. You're actually Lipschitz continuous in both directions. So if you've got a linear homeomorphism, it's actually Lipschitz continuous in both directions, and under those circumstances, one space is complete if and only if the other is. So already, isomorphic as norm spaces, so this is isomorphic as norm spaces, i.e. with using a linear homeomorphism. Then one of them is complete if and only if the other is. Of course, I don't mean that if you've got 2 norm spaces that are isomorphic as vector spaces, that one's complete if and only if the other is. That would be nonsense. Now, isometrically isomorphic is such a strong condition that we usually regard the things as essentially identical. But having said that, that R squared norm 1, R squared norm infinity example, which is a bit of a fluke, I don't normally regard those as being identical, but they just happen to be isometrically isomorphic. But under most circumstances, things that turn out to be isometrically isomorphic are so for some sort of natural reason, more natural than that setting. And people do have a tendency to write equals. So this will come up when we do duality, when we say the dual of this space is that space. Well, it isn't really. It's just isometrically isomorphic to it in some particularly easy way. So we're going to say the topological dual space of little c0 is little L1. Well, actually, what that means is it's isometrically isomorphic to little L1, and so on. We'll come back to these dual spaces later. And that brings us to the end of that section. Any questions about isomorphisms? No, I didn't, but it can happen. No, I don't deliberately write tongue twisters, but if you're not watching out for it, it can happen. Which one in particular? Linearly homeomorphic and isometrically isomorphic. And sorry? Remark B. Let's have a look at that tongue twister. Why not? Where are we? The inverse of a surjective isometry is automatically an isometry, so the inverse of an isometric isomorphism is also an isometric isomorphism. I can say that. There you go. Okay, so I don't think it's such a bad tongue twister. Could have been worse. Right, let's stop that there.